So our next speaker is Erik Lamoureux. Erik is an individual who's in a much better mood these days now that he's recently defended his PhD in mechanical engineering. So you can tell when you see him in the hall, he has a certain bounce in his step, and so that's very nice to see. He'll be speaking to us today about red blood cell deformability in chronic transfusion recipients. Erik, thanks.
Thanks very much for that introduction, Dr. Kim. As he mentioned, I'll talk about red blood cell deformability as a biomarker to predict circulatory clearance time in chronic transfusion recipients. So the motivation behind this is that red blood cell deformability is vital for circulation through the body. As red blood cells age and as they get damaged during storage, they lose that deformability, causing them to be more susceptible to being caught in the microvasculature, inhibiting gas exchange, and then they're targeted for elimination. And as Dr. Cron mentioned earlier, regular transfusions being given to patients leads to iron overload, and these have multiple complications, including endocrine effects, liver effects, and damage to the heart. So the idea would be to identify cells that have more deformability, might last longer in circulation, and try to avoid some of these iron overload effects. So the approach we took for the study is shown here. So we took segments from blood bags, and we put these through a microfluidic sorting device. This squeezed the red blood cells and was able to produce deformability profiles for each donor. Then we measured the hemoglobin at the next transfusion, 21 days later typically, and then mapped out that hemoglobin, which is a measure of their circulation longevity, versus the transfusion rigidity, where we would assume that more rigid transfusions would be associated with lower hemoglobin. Then we would look at a subset of the more deformable cells and project out the extended circulation time. And so here are what our results look like. On the left are the data for donor blood bags. So each dot is an individual blood bag, where we have donor rigidity score on the x-axis and hemoglobin 21 days later on the y. And we see an association with more rigid donor blood bags being associated with lower hemoglobin transfusions, and more rigid over here, and more deformable being associated with higher hemoglobin. But each transfusion has about 2.4 blood bags in it on average. So if we average out the rigidity score of each blood bag, we see the chart on the right here, which maintains the same relationship with a mild but significant relationship where more rigid transfusions are associated with lower hemoglobin after transfusion. And when we break this down into rigidity score ranges, we see that the most rigid samples, those with rigidity scores over 3.0, were significantly lower than the other deformability cohorts, indicating the most rigid cells are associated with worse transfusion outcomes. And I apologize for a messy slide here, but I'll walk through each of these charts. So starting on the top left here these are projected hemoglobin cycles for a transfusion dependent patient. We see that they come in, their hemoglobin's measured, they receive a transfusion, it gets incremented, and then it decreases linearly until their next transfusion. We observe some transfusions that rapidly clear out of the body very quickly, and others that clear much more slowly. So our idea here was to see if deformability was associated with those different elimination cycles. So zooming in on one of those transfusion cycles, again, we have the pre-transfusion hemoglobin, the transfusion hemoglobin increment, the hemoglobin consumption over 21 days, and then their measured post-transfusion hemoglobin. So shown on the right here, the black line is the average hemoglobin cycle for all of our patients. There's a 10 transfusion-dependent beta thalassemia patients. We looked at 55 transfusions, and we see the black line is that standard cycle. And then if we select the top 25% most deformable transfusions, that results in an elevated hemoglobin 21 days later, extending out that circulation time by 17%. And if we wanted to adjust what that threshold was, we would see this chart on the right here, where if we included all the transfusions, it's no different than baseline. And as we slowly move this threshold to the left, including more and more deformable cells, we see a linear relationship with more deformable cells being included, being associated with longer transfusion longevity. We also noticed that different patients responded to transfusions and to different levels of deformability differently. So we see that same hemoglobin versus rigidity score plot here, but broken down by each patient. Each color is a different patient seen in our study. And we use statistical modeling to use the overall trend and borrow patient-specific trends to get patient-specific trend lines. Using this approach, reduce the mean absolute error in the hemoglobin prediction for 7 out of 10 patients. And when we compare the true hemoglobin versus the predicted hemoglobin using these new patient-specific models, we see that the perfect prediction line of our relationship exactly matching, or the trend line exactly matching the perfect prediction line. And for reference, this relationship is about 0.3 correlation if you don't account for those patient-specific differences. So in summary, this work looked at microfluidic sorting, which enabled the sensitive measurement of red blood cell deformability. We found that more deformable red blood cells were associated with elevated patient hemoglobin levels 21 days later. We found that using patient-specific adjustments for this modeling resulted in improved predictions, and this was the first time where donor red blood cell deformability had been shown to be related to post-transfusion outcome in transfusion-dependent patients. Thanks, everyone, for listening.
Erik, thanks very much. Question about rigidity. Is rigidity itself, is the scale, is it linear or logarithmic?
I would say it's a little bit complicated. Okay. How we derive this rigidity score is based on this microfluidic device, which I've kind of glossed over the details here. But there are 12 outlets of this microfluidic device, and about 4 or so outlets are where the cells are sorted to. These cells differ in width by 0.25 microns. So in that sense, it is linear. Outlet 2 is 0.25 microns narrower than outlet 3, and so on. And then, those create normal distributions. We translate them into cumulative distribution plots to get a distinct single rigidity score per donor. So I would say it's roughly a linear relationship.
Thank you very much for a very interesting presentation. The question that I have is, do you see any difference in red blood cell deformability in the age and sex of the donors?
Yeah, thanks for the question. I don't believe we looked at. We did look at age. We found no relationship between age of donor and differences in rigidity or hemoglobin outcome. We did see differences between men and women. Generally speaking, in our study, female donors were associated with lower hemoglobin outcomes, but no difference between male and female donors and the rigidity scores.
And what about the age of the red blood cell? Did you check that?
We didn't look at age of the red blood cells. It's quite difficult to get red blood cell subpopulations, but there are differences in the age of red blood cells based on the age of the donors. Some work by Dr. Acker in Alberta has shown that young teenage male donors in particular have biologically older cells, which are worse for transfusion. So there is some relationship there, but we didn't look at it specifically.
Hi, just comment on the patient-related, specific patient-specific characteristics. Can you comment on that?
Yeah, sure. So, red blood cell deformability depends on patient factors like age, diet, sex, genetics, things like this, and also different patients just have different experiences with beta thalassemia. Some are more severe than others. For instance, if we look at This patient in blue here, consistently their hemoglobin is a lot lower than the trend line. And, the purple patient up here has much higher hemoglobin than the trend line. So I believe this chart is just showing different disease severities, and that is the majority of the trends that we see. These lines, the slope doesn't change too much. The slope changes a little bit, and that's based on their different responses to the deformability, but the main change we see is where that y-intercept is, and I believe it's just differences in disease severity. Sure.
I just have a couple questions. Sorry, it's a little bit hard to see from back here, but could you just remind me what the sample sizes of your analyses were and effect sizes, and whether you have any recommendations as to how your findings can be implemented in the field? Thank you.
Yeah, no, good question. I did gloss over this, but our sample size was 10 transfusion-dependent beta thalassemia patients. We looked at 55 transfusions comprised of 131 donor blood bags. So it's a decent sample size here, although, didn't see a ton of patient variation given only 10 patients. If we looked at effect sizes, I don't know if I did it specifically for this study, but I did it for a similar study. But you see moderate to strong effect sizes between deformable and less deformable cells in terms of hemoglobin outcome. So it is a significant difference that is observed here. It's difficult to translate this specific study to the clinic because it requires the use of this microfluidic device. If I'm working full time, for a full week, I can make maybe 20 microfluidic devices, something of that order. And these are non-reusable, single-use devices. We usually run them in duplicates so we can verify that the manufacturing and the sorting is consistent. So that would mean, 10 donors per week could be analyzed. That's, not great throughput in a clinical setting. There might be ways to have more commercial instead of bespoke, microfabrication techniques to make this a little bit more accessible. But what our group has started moving towards is using AI image analysis of cells. We've been taking donor blood, putting it into smears, imaging it, and then using AI to predict the hemoglobin outcomes just from those cell images. And that gets at least as good of results here, often even better. And that's much more accessible. You just need a microscope, blood smears, and then a moderately powerful computer. So we're moving towards a clinical study where we will sort donor blood for beta thalassemia patients, giving them the ones that the AI model predicts to be long-lasting, and then comparing that to the controls and seeing what the actual effect size difference is. If we just go here, Dr. Cron mentioned in her presentation, but luspatercept, 21% of patients see at least a 33% reduction in their transfusion outcome. Combining that together, that's about a 7% improvement in longevity over the population. So we use that kind of as a benchmark for success. So at least in this study, 25% or so of the most deformable cells meet or exceed that target. And similarly with the AI study, identifying the more deformed or the longer lasting transfusions has similar clinical effect that we're projecting, and that'll be the target for our clinical study to evaluate whether this is clinically meaningful.
Erik, wonderful presentation. I guess I'm interested in the concept of a super donor based on deformability. Is there any way you can get a simpler way of assessing deformability other than your rather exotic device that has practical limitations?
Yeah, thanks. So we didn't, at least right here, we didn't really identify many super donors. Mostly what we observed is just the most rigid cells. Donors who had more rigid cells were associated with lower outcomes. We saw less benefit at the very high end. If we look at the most deformable samples here, they're not so much different from the ones just next to it in the middle. So we weren't able to capture that. As I mentioned, with this AI analysis that can predict transfusion outcome, it's also able to predict deformability at a very similar accuracy of our microfluidic device. So that might be another avenue to identify the biophysical properties of these cells.
Thank you.
do you see the same pattern with the same donor over and over again? Like, you know, are there genetic factors for having a patient, a donor having more rigid cells, or is there some coming from that angle? Yeah.
Yeah, so in this study in particular, we didn't track the same donor over time and see how their transfusions, you know, or how the donations affected transfusions. I just think, you know, with 131 donor blood bags taken over a year, I think the chance of a repeat donor having their blood being allocated into the same pool for these patients was low. So we didn't look at that specifically. However, we have looked at you know, members of our lab and other volunteers to donate blood and check their deformability, and we generally see stable deformability levels. They can change, you know, if someone goes on new medication or their lifestyle factors change, that can affect the deformability, but generally speaking, we see it to be quite consistent.
Great talk, Erik. So one question regarding the sampling of your samples. You took the samples from the blood bag, or did you take the samples from the segments of the tubings?
Yeah.
If you took from the segments, which segment did you took? You took from the segment which is closer to the bag, or a segment which is far away from the bag? So you have 8 segments, am I right, in the tubings? Did you take the segment which is closer to the bag, or you take the segment which is away from the bag, far away from the bag?
So yeah, we did sample segments and not blood bags. That was to not compromise the safety of those bags with sampling. I don't know exactly where along the chain we received the segments from. These were provided to us at St. Paul's, so I don't know exactly where. I do know that we noticed early on in our study the segments we received were quite small, and we believe that the heat from the gun that was segmenting them off was damaging the cells. We were observing additional hemolysis. So we asked for larger and more segments for each sample. So we received about 3 segments, kind of about 8 centimeters or so across to do our sampling, and we mixed them together to get a characteristic sample. But they were 3 links next to each other, but I don't know where along the segment they were taken from.
Thank you.
Okay, thanks everyone.